Each year, volcanoes unleash their furious energy, hurling hot ash and pouring deadly clouds of gas below. On their flanks, no living thing stands a chance when 1,200-degree lava ignites the surrounding countryside. What draws people back to the slopes of these incredibly dangerous volcanoes? Is it the promise of fertile soils to grow food? Is it the vast store of easily accessible steam energy lying just below the surface? Or is it a society's tradition that draws people to the mysterious power of the volcano? Today, nearly 400 million people live in the shadows of active volcanoes, people living on the ashes of destruction. Volcanoes, understanding the hazards. Dr. Dan Miller with the U.S. Geological Survey is a volcanologist, an earth scientist who specializes in the study of volcanoes and the effects they have on people and property around the world.
More than 1,300 volcanoes on the surface of the Earth have erupted in the last 10,000 years. This is certainly a minimum number because there are many volcanoes that are still undiscovered or unstudied, or their eruptions are undated. At least a quarter of those have caused fatalities. So many of these eruptions have been very deadly and very destructive. And most of the fatalities have occurred in areas on Earth where there are many volcanoes, where they tend to erupt explosively, where they tend to erupt frequently, and where there are large concentrations of people. And such places include the islands of Indonesia, the Philippines, Japan, central Italy, parts of Central and South America, and parts of the West Indies, the Lesser Antilles. And in each of these cases, there are very explosive volcanoes. They have erupted frequently in the past, and therefore we expect they will erupt again in the future, and probably repeatedly in the future. And because of the rich volcanic soils and because of limited space on some of these island countries, they are literally covered with people, very densely populated.
What causes volcanoes? Where do they occur? And why are some more dangerous than others? By itself, a single volcano appears to be an isolated feature on the Earth's surface. But when we plot the location of volcanoes on a world map, a definite relationship becomes obvious. What's even more interesting is that a similar pattern emerges when the world's active earthquakes are plotted in the same way. Is it coincidence, or does some process closely connect these two phenomena? Interestingly enough, the pattern outlines the edges of thin tectonic plates, rigid pieces of the Earth's crust that form the continents and the ocean floor. Like a cracked eggshell, these tectonic plates move slowly over a more dense and hotter region of the Earth's interior called the mantle. Boiling convective motion within the mantle pushes, pulls, and grinds crustal plates against one another. It's at these places where we find most volcanoes. Let's study them one at a time. The first setting in which we find volcanoes are where tectonic plates collide with one another. Geologists believe that when crustal plates converge, the denser one sinks beneath the less dense plate along great faults called subduction zones. Here, friction produced by the dragging motion of the downgoing plate generates deep earthquakes and melts the descending crust to form magma. Because magma is less dense than its surroundings, it rises like hot bubbles, erupting at the surface to form active volcanoes. Because these magmas are rich in dissolved gases, they tend to erupt explosively. Soda pop erupts like a volcano too, especially when pressure is relieved, causing gas to rapidly escape from the bottle. The world's most dangerous volcanoes form at these converging tectonic plates, creating a circular pattern around the Pacific Ocean, an arrangement scientists refer to as the Ring of Fire. The second location in which we find volcanoes occurs where crustal plates are separating. Unlike those at convergent plate boundaries, these volcanoes tend to erupt less explosively because the lava contains so little dissolved gas. The ocean's crust is built almost entirely from lava, which oozes from great fractures along a sinuous 45,000-kilometer-long chain of mid-ocean ridge volcanoes. Surtsey, an impressive new landmass, was born from eruptions along the undersea North Atlantic Ridge. Finally, a third type of volcano occurs within the boundaries of tectonic plates. Scientists think that volcanoes within plates are generated by long-lived heat sources, or hotspots. Magmas generated at hotspots melt their way through the Earth's outer crust to produce intense regions of volcanic activity. The best example are the Hawaiian Islands. Here, the slow movement of the Pacific Plate over a fixed hotspot has resulted in a chain of progressively younger volcanoes. One of the youngest, Kilauea, erupts with remarkable frequency. Kilauea's dark fluid-like lava cools to form the most common volcanic rock, basalt. It can erupt as spectacular fountains of red-hot lava, or quietly form pools and lava lakes that overflow as lava rivers and cascade as spectacular lava falls. When a volcano erupts, why are geologists willing to risk their lives in the presence of one of nature's most sensational events?
First of all, volcanoes essentially are a window into the inside of the Earth. Since we can't go inside the Earth and find out what's going on down there, we sort of have to wait on the surface of the Earth and let volcanoes bring these materials up to the surface. The lavas that erupt at the surface originated as magmas, and as magma moves, it makes lots of noise. And we recognize the noise as earthquakes. So there are various kinds of earthquakes generated underneath a volcano as magma is moving towards the surface. These earthquakes and these kinds of tremor are typically studied using what we call seismometers. This is an instrument that you place on the ground, and it detects very small motions or movements of the ground surface. The information is interpreted at the Volcano Observatory in order to locate where these earthquakes are occurring, to figure out how deep these earthquakes are, and to look at the character of the earthquakes. In addition to seismic monitoring, there is another way of recognizing that magma is moving toward the surface. And that is that as magma gets toward the surface, it causes deformation or stretching or bulging at the surface of the Earth. And so what scientists are looking for when they monitor volcanoes are those earthquakes to become shallower with time as magma gets closer to the surface. And we look for increasing rates of deformation at the surface around the volcano, which indicates that magma is getting very close.
A striking example of how early warning signs alerted volcanologists of an impending crisis occurred in the months leading up to the 1980 eruption of Washington State's Mount St. Helens. Seismic activity, which began in March of 1980, became progressively more frequent, and the earthquakes became shallower. By early May, scientists estimated magma had moved to within a kilometer of the Earth's surface and was now causing the north side of the mountain to bulge dangerously. Small but frequent eruptions dusted the glaciers with ash and produced a rapidly expanding crater at the summit of the volcano. Because of these increasingly alarming signals, scientists hypothesized that a major eruption was imminent. On May 18, 1980, Mount St. Helens exploded violently, removing the top 400 meters of the volcano's cone in only a matter of minutes. A U.S. Geological Survey map published the following year illustrated the distribution of various Earth materials left behind by the massive eruption of Mount St. Helens. They include lava, and in Mount St. Helens' case, a dome of lava, pyroclastic flows, mud flows, and deposits of ash. Dr. Miller explains how for most volcanoes, some variation of each of these hazards has a unique impact on life and property.
Lava flows typically are not very hazardous. Most lava flows can be outwalked by people, and certainly all of them can be outrun by people. So lava flows rarely kill people, but they do destroy non-movable property. Pyroclastic flows are basically mixtures of hot, dry rock fragments and hot gases that move away from volcanoes at very high speeds. They move at speeds of hundreds of kilometers per hour. Once a pyroclastic flow begins at a volcano, anybody that hasn't escaped is likely to be killed. You can't even drive a car fast enough to get out of their way. It's the most destructive and hazardous process that occurs at a volcano. Finally, in many cases, volcanic materials or fragments that are generated at the volcano are mixed with water, and they flow down the slopes of a volcano as usually a wet mixture, sometimes a hot wet mixture of volcanic debris and water. These things we call mud flows. They have the consistency of wet concrete, and they move down valleys at a few tens of kilometers per hour, but often over a period of hours they can move hundreds of kilometers away from a volcano. And there basically are no works of man, no matter how heavy or how big they are, including large houses and so forth, that can't be carried away and or destroyed by mud flows.
But materials that flow from volcanoes are not the only hazards. Tephra, or fragments of lava and rock blasted into the air, can affect much larger areas. In 1991, the spectacular eruptions of Mount Pinatubo in the Philippines ejected an estimated 3 cubic kilometers of tephra into the sky. The finest particles were carried 40,000 meters high as billowing columns of gray ash. Near the volcano, ash blackened the sky for hours, turning day into night and clogging the air with fine particles of pumice and ash. Downwind, thick pyroclastic and ashfall deposits covered the land like blankets of gray snow. These roofs of aircraft hangars at nearby Clark Air Force Base caved in from the crushing weight of Pinatubo's heavy ash. Although damage to property was extensive, relatively few deaths occurred. The reason? For several months before the eruption, Filipino and American scientists carefully monitored Pinatubo's seismicity and convinced over 50,000 residents to evacuate their homes. Had they not been warned soon enough, Pinatubo could have caused the most fatalities of any eruption in modern times. But sometimes scientists' warnings go unheeded, and the results can be tragic.
One of those eruptions occurred in 1985 in Colombia at a volcano called Nevado del Ruiz. And although the eruption was relatively small in volume, it erupted hot materials out onto the glaciers and ice fields in the summit area. And these hot chunks of lava and rock caused very rapid melting and generated mud flows. And one such place was the village of Armero, a village that was populated by about 25,000 people. And these mud flows destroyed most of the village and killed more than 23,000 people. It turns out that in 1985, Ruiz volcano showed all kinds of unrest. There were swarms of earthquakes occurring under the volcano. We suspect there was deformation of the volcano. There were steam explosions that occurred prior to the big eruption that was so destructive. We as scientists learned a real lesson there. We have learned that it's not enough to monitor volcanoes. We also need to be able to communicate that information to the officials, to the people who make the decisions, and to the populace as a whole.
As dangerous as Mount St. Helens and Mount Pinatubo may seem, they pale in significance with other eruptions that have occurred on Earth. Some have been 100 times more powerful than Mount Pinatubo, blanketing ash across continent-sized areas and blocking sunlight for weeks at a time. Could such a cataclysmic eruption occur today? At Yellowstone Park in the western United States, 3 colossal eruptions within the last 2 million years produced incredibly thick lava and pyroclastic flows. Ash was deposited as far as the Mississippi River. If indeed Yellowstone should erupt once more, how many lives would be lost by mud flows and enormous floods? Would food production in the American Midwest be snuffed out by crop-damaging ash? And would gases from the eruption send our climate into another ice age? For Earth scientists who specialize in studying volcanoes, the obvious challenge is to identify potential eruptions and provide timely warnings. The hazards from lava, mud, or from pyroclastic flow deposits are incredibly terrifying, especially for people who live along the margins of Earth's most active tectonic plates. Other hazards are less immediately obvious, but they can impact life on our planet over longer periods of time. Global encircling ash and volcanic gas may change our climate or even threaten Earth's protective layer of ozone. But perhaps the most difficult challenge of all is not scientific. Rather, it's the responsibility of educating an ever-growing population about volcanic hazards.